Week 10, Problem 5. Transverse waves are being generated on a rope under constant tension. Determine the factor by which the acquired power is changed in each of the following situations. Alright, I have a feeling this is just going to be a straight power in a string wave. Bam. Power transported by a string wave. Come on, hyperphysics. Fail me again. Fail me again. Nope, too slow. There we go. Right there. 1/2 mu omega squared amplitude squared. That's from hyperphysics. Oh my god. Okay. So hyperphysics did not fail me this time. Alright. So, moving over here. Power equals 1/2 omega is it amplitude squared? Omega squared amplitude squared? That's mu, not omega. Omega squared amplitude squared times velocity. Alright, so to talk through these guys, I'll make a little arrow there. Not because it's actually a vector, I guess it probably is, but because that way I don't get it confused with voltage. Not that not that we are using voltage here, but just keep things cleaner. All right, so talk through this guy real quick. 1/2 mu is mass per unit length. Omega is the angular velocity. A is amplitude, and V is the speed of propagation. Actually, I think they said it here too. Power transmitted, angular frequency, mass per unit length, wave amplitude. Yep, got it. So, you probably have the skills to actually derive this if you cared to. I wouldn't bother, but this is basically the same as the equation for kinetic energy divided by time. So you have omega, which is kind of like velocity. You have mu, which is mass per unit length. You have 1/2, so this is kind of like 1/2 mv squared right here, which you're used to with the kinetic equation. And then to get the power, you have a velocity, which is meters per second. And there's probably some other details there, and that's just kind of a basic idea of where they're coming from with this equation. All right, so the length of rope is doubled, and the angular frequency remains constant. So the length of rope is doubled. All right, so I'm going to take this equation, copy, paste, bam. I'm going to rewrite mu as mass per unit length. So the length is doubled, but then so is the mass, because it's a mass per unit length. So when we double this, we have the mass doubles, but then the length, because the length doubles. So the length of the rope is doubled. Okay, so they said length of the rope doubled, but like the mass stayed the same, like you just have a thinner rope, then that would make a difference. But that's not what they said. So the length of rope is doubled, and the angular frequency remains the same. So the top part doubles, the bottom part doubles, and everything else is the same. So I'm going to say final divided by initial is 1, because final equals initial. All right, so we got that guy done. Kill this guy. Die. Didn't quite get them all. There we go. But then, let's see. Copy paste. I should have just, there's probably an easier way to do that. Oh well. Actually, I'm going to put my safe equation up here. That way I can just use that guy. Both the length of the rope and the wavelength are halved. Okay? And for some reason that one's wrong. Just assume that the mass stayed the same, but the length, I don't know. Both the length of the rope and the wavelength are halved. Okay. So, rewriting this guy again. I'm going to say mass over length. So, the length of the rope is halved. So this guy goes to 1/2. But I'm also going to assume that the mass of the rope is one halved as well. And the wavelength. Okay. So omega equals 2 pi f, where we know that velocity equals distance divided by time, because my car goes in miles per hour, which equals wavelength times frequency. Therefore, frequency equals velocity divided by wavelength. So omega equals 2 pi v over lambda. Okay? So then here we're just going to do 1/2 m over L 2 pi v over lambda squared amplitude squared velocity. Okay. So they said change this to some sort of blue. Here we go. So they said length goes to 1/2, which I'm going to assume also means the mass goes to 1/2, so it doesn't matter because it's mass per unit length. And then they're going to say the wavelength goes to half. So if the wavelength sits on the bottom halves, it's going to make power go up. So it's going to raise power. So there's really two wavelengths here. So each half of the halving of the wavelength is going to double the power. So power is going to go up by a factor of 4. So it's basically like saying 1 divided by 0.5 quantity squared, which is 4. So I'm going to say that the final will then be 4 times as big as the initial. And it does make sense that if you may have smaller wavelengths, so if you have a rope and you're making waves like this, to get smaller wavelengths, you're going to have to do it a lot faster, which is going to take more effort, which will probably mean more power. Right? The angular frequency is halved, and the oh no, I'm going to erase this guy. Oh, there we go. You can go away. There we go. Oh, I didn't even know that function existed. I had no idea what that happened. There we go. All right, back to the problem. The angular frequency is halved and the amplitude is doubled. Right, so amplitude doubles and the angular frequency is halved. So we're going to have angular frequency. Okay, so this is the angular frequency, which is not the same as normal frequency. All right, so we have 1/2 squared plus 2 squared, which are going to cancel each other out. So we're going to get a total of 1. The final and the initial will be the same. Both the amplitude and the wavelength are halved. Okay, so going back to what we did in a couple problems ago, we're going to have 1/2 m over L, because that's what mu is. And we're going to have 2 pi v over wavelength, because that's what omega is, angular frequency. And we're going to have amplitude still and v. So both the amplitude and wavelength are halved. So when we have the wavelength, we're going to have 1/2, and we're going to square that, which is going to become 1/4. So when we divide by 1/4, that's going to be the same as multiplying by 4. And then amplitude is halved. No. Yep, and the amplitude is halved. So it's going to be 1/2 squared, which is going to be 1/4. So we're going to have 4 times 1/4. So final divided by initial is going to be 1. So it all cancels out. All right. And again, if for some reason, throw in the comments below, help out the team. If when they're saying that they have the length, they don't mean that the mass is also halved, then some of these guys will be off. The same method will work through when you guys are working through these problems. All right, sound good? This one shouldn't be too tough. I imagine you won't get too many power problems. We'll see. All right, on to problem 6.